Hi, this is Roger. I'm geologist and I'm telling you a story in 3 chapters. Each of the chapter is a separate YouTube movie dedicated to the 3 topics listed here. The story I'm going to tell you is based on research works which are published in the 3 papers listed at the bottom. As a young geologist, I worked in the Sultanate of Oman, and there I did field studies for my master thesis, which was about Pan-African granites. Then I did my PhD study in northern Italy in the so-called Strona-Ceneri zone, where I actually developed most of the ideas and concepts I'm going to speak about in these movies. During my PhD study, I got a travel grant to visit the Lachlan Fault Belt in Australia, and I did a comparison of the Lachlan granitoids, which were thoroughly studied by Chappell and White. And by the way, I met these 2 guys, which was very impressive to me. And I compared these Lachlan granitoids to the Ordovician Orogeny in the Strona-Ceneri zone. And this comparison actually became a base for my new concept and new models. Today, I'm doing fieldworks mainly in the Alps, in the Gotthard Massif or other polycrystalline pre-alpine basements. If you have questions or comments, you can contact me, and for that, I have listed my coordinates in this slide. I like to start with this figure. In the lower part, we see the situation today. In blue, there are the subduction zones, here along the Ring of Fire. And in green, we have the regions where we have a large input of sediments deriving from the continents. Today, there is almost no overlap between these 2 types of regions, with one exception in the Gulf of Alaska. There are a lot of terrigenous sediments overlapping with a subduction zone. Now, this was fundamentally different in the early Paleozoic era. There we had a circumgondwanan subduction system, and in the same locations we had a tremendous sediment input from Gondwana, sediments which derived from the eroding Pan-African belts. This situation is the frame for my story I'm going to tell you. This is a very similar figure, but with more details. It's again the early Paleozoic situation. Here we had the South Pole at this time. We have all these Pan-African belts in between the cratons. And these arrows, they symbolize the transport of sediments towards the circumgondwanan subduction systems. The base for this figure is taken from many publications of other researchers, but for me, these 2 papers were really key. The first one dealing about the tremendous amount of sediments derived from the Pan-African belts, and the second one drawing this picture of a circumgondwanan subduction system. This is a key figure. It summarizes what happens when a subduction zone is fed by a lot of sediments. And I show this in 4 steps from A to D. And figure A is about the situation we have in the Andean arc. So we have the subduction of the Pacific plate. There is a cold accretionary prism. And here we have the subduction-related magmatic arc, which is dominantly a metaluminous arc. So we have granites which evolve by fractionated crystallization of basaltic magmas, but there is also contamination from continental crust. But this is about the situation we know, we can observe today. Now in the Gulf of Alaska, there's a particular situation where the sediment input is quite large, so that the subduction-related magmas are intruding parts of the accretionary complex. And Barker et al., they called these 4-arc magmatism because these granitoids and these volcanoes are in front of the main arc. Now what happens at the base of an accretionary complex, which is intruded by primary basalts, is very important to understand for everything which will follow in the couple of next minutes. What you see here is that the intrusion of these hot magmas causes the isograt, which is for 500 degrees C, starts to being elevated. And these high temperatures, they cause the sediments to melt to a large extent. And this is going to dominate the chemistry of the magmatism, which is then becoming more and more periluminous. Now, if we imagine that the sediment input was even larger by a factor of 10, which is probably the case for the early Paleozoic, then these accretionary complexes, they start to grow laterally versus the ocean. And the whole magmatic arc is far away from the rim of the continent. And this type of lateral growing of a continent without developing a high range, a high mountain range, this we call subduction-accretion complexes, which are in situ cratonizing. What is meant by this cratonizing? It means that we are not building a high mountain range like the Andean belt, which is going to be eroded. No, we grow laterally, and the volcanoes and the incoming sediments, they are rapidly recycled and being eroded and redeposited in the trench again. So we have very fast cycles, which cause that this type of crust formation is laterally growing. It's a kind of recycling of detritus coming from the continent and making the continent growing towards the ocean. This is the model which I think caused Gondwana to grow at its periphery in early Paleozoic times. What I showed in the last slide, I'm going to show in an animation of in total 16 slides. This one is the first of this series. And it shows again what happens if an accretionary wedge, which is here relatively small, at the rim of a craton, what happens if this wedge is going to grow because the sediment input grows. What we see here is, again, the situation in the Andean arc, where we have the subduction of the Pacific plate. We have the basalts, which are rising and which are evolving into a metaluminous magmatic arc. By the way, you have all the legends down here, and this legend is kept for the entire series of 16 slides. Important is that we have a small cold accretionary wedge. Now, we can grow the input of sediments to a certain extent as long as the primary subduction-related magmas are intruding this main arc. Nothing changes. Nothing changes until the sediment input, like in the Gulf of Alaska today, grows in size until the magmas start to intrude the base of the accreted sediments. And imagine what happens if we develop temperatures of 700, 800, 900 degrees in a gray wacky system. And that is what can be observed today in the Gulf of Alaska. We start melting these gray wackies. These melts raise as diapirs and intrude the middle and higher up parts of the accretionary complex and partially extrude as volcanics. And at this point, the accretionary complex becomes hot. So it changes from cold to become hot. And as a result of that, the magmas intrude the accretionary complex, the arc migrates from the rim of the craton into the accretionary complex. And by that, it changes its chemistry from dominantly metaluminous to mainly periluminous, in this case also called four-arc granitoids, because they are, from a geographic point of view, in front of the main arc. Now, in the early Paleozoic, the sediment input was so large that these accretionary complexes started to grow oceanwards. And by that, the volcanic arc became located totally within these accretionary complexes. And what is important is that we do not develop a high mountain range, but we develop a series of volcanics which got very quickly eroded again and recycled again. And Barker et al., they have shown for the situation in the Gulf of Alaska that the petrogenetic cycles are very fast. They are in the range of 5 million years. And this is what happened in the Cenerian Orogeny. So the Cenerian Orogeny is the Ordovician event which generated the continental crust in the region of the Alps or in other parts of southern Europe at the northern periphery of Gondwana. With growing input of sediments, these complexes grow for hundreds or even thousands of kilometers in width versus the oceans. And as these magmas, these periluminous granitoids solidify and being sheared at the same time, so tectonics is another important parameter, these bodies become orthogneisses. Orthogneisses which we today can observe in the pre-alpine polycrystalline basement units generated in the early Paleozoic. To visualize the mechanisms within a cratonizing subduction-accretion complex, I make here a comparison of three types of orogens. The alpine type, where we collide two continents. The Andean type, where an oceanic plate is subducted below the rim of a continent with a magmatic arc. And a similar situation called the Alaskan type, similar to the Andean type, but with a much larger sediment input. And here you have a table with different criteria to visualize what are the main differences between these three types of orogenies. So the sediment flux can be optionally here, but is essentially to develop cratonizing subduction accretion complexes. Important is that crust, which is older than the orogeny itself, is actually the main material which is here colliding and stacked to build high mountain ranges. Or here, the older crust is the host for the intruding granitoids. But here, the older crust is far away, hundreds of kilometers back in the hinterland, and we are within the accreted sediments. The main structures here in the alpine type are nappes, which are stacked. Here we have steep shear zones developing steep planar structures. And here we have intrusive contacts as main features. In collisional type of orogens, we have few magmatites, like in the Alps. Alpine magmatites are quite rare. In these two systems, we have actually arcs, which are either metaluminous or which are periluminous, because here the melting of the accreted sediments is the main source, the main material source for the granitides. Regarding isostasy and topography, we develop here high mountain ranges like the Himalaya, or here like the Andean, the Cordillera range. Here, we don't produce high mountain ranges because this orogen is laterally growing and not vertically. Therefore, this in situ cratonization causes that the subduction accretion complexes, as they are generated and being stabilized during the periluminous arc magmatism, they are stable, they stay as such, and the lower middle crust is not coming to the surface unless there is a younger collision, which is different in the other types of orogens. The erosion and exhumation, I wrote here weak. That's actually not true. The erosion is instantaneous. So this orogen has never the chance to develop a high mountain range because these soft sediments, these soft volcanics are readily eroded by the first rainfall. And they are redeposited in the trench and recycled again. And that's what listed here. So we have actually the recycling of sediments which come from an older continent. Here we have little generation of new material. Here we have the opposite. We produce a lot of new material. And here we are somewhere in the middle, because we have this situation of an Andean situation, but we mainly recycle crustal material. And examples of orogenies in the Paleozoic are the Caledonian, the Cenerian, and the Cadomian. These three papers listed at the bottom were key papers for my studies. And together with my studies I did in my PhD works in the 90s, I developed the concept for subduction-accretion complexes as a model for the Cenerian Orogeny. Barker et al. Was important for me because they studied the 4-arc granitoids in the Gulf of Alaska. They showed how fast the petrogenetic cycles are. They criticize the classical granite classification schemes, because instead of looking what is the chemical fingerprint and attributing that to a predefined tectonic setting, they said we have to consider that we are melting sediments which bring their own inherited signature from the hinterland. And this inherited signature is again inherited to the peroluminous granitoids, which are generated by the melting of these sediments. So this inheritance of isotopic and chemical signatures is very important and should make us rethink about very classical chemical discrimination diagrams for granitoids. Therefore, I became attracted by the granite classification of Debon and Lefort, where there is a pure descriptive manner of treating compositions and grouping and attributing granitoids on the base of their chemistry and mineralogy, without applying predefined tectonic settings. And most important was the paper of Keith Crook from 1980. He developed actually the concept of cratonizing subduction-accretion complexes for the Lachland fault belt. And that paper inspired me a lot when I did my PhD study. This is Professor Dr. Ivan Mercoli. He was my teacher, professor. He was my supervisor during my master thesis in the Sultanate of Oman. And he became a friend and my most important mentor during the development of my models. Actually, I developed my models in the constant dialogue with him. So he was my main person with whom I could share my ideas and let these ideas to becoming mature in our discussions. And unfortunately, he died in 2019. And yeah, I really miss him. He was a great human, a great friend, and he was a very good geologist. Without him, I would not be able to tell you this story. Thank you very much, Ivan. So here we are at the end of my first chapter. I hope you enjoyed. I hope you got inspired as I became inspired by the research works of others. I think that is the main purpose of doing science, to take ideas from others, to add new questions, new observations, and to further develop existing thoughts of others and applying them to new situations we observe in the field. And that's the way we can make progress in science. So we're not speaking about truth, we're speaking about models which are able to explain our observations. I hope you enjoyed, and if you did, then go to the second chapter and third chapter of my research outcome. Thank you very much.